reinforced concrete design. Concrete structures widely used around the globe for construction of residential, industrial, and infrastructure projects due to their advantages. Concrete is strong in compression and steel is strong in tensile strength. Hence, steel used in the form of bars to made as a reinforced concrete to give combined benefits of compression and tension. This effectively resists the external loads. So, reinforced concrete strictly as a composite material includes cement, sand, aggregate. It required special attention and some assumptions to acquire the full strength out of it. So, percentage of each material, water cement ratio, percentage of the steel will play the major role on strength and durability of the concrete. In limit state design, partial factors are used to consider for possible deviation of the strength due to the manufacturing, accuracy of calculations, future risk to life, and economic aspects. The factors are 1.5 for concrete and 1.15 for steel. Concrete is more due to the fact that concrete is made up with many ingredients as discussed like cement, sand, aggregate, and admixtures. So it is a composite material mixed as a single compound. It has given higher factor compared to the steel as it is manufacturing is mission made. The stress strain curve parabolic up to the strain of 2% or 0.002 as shown in the picture. Thereafter remain constant up to 0.0035 of strain. So this is the straight line. Due to some practical experimental results, it may vary, but assumptions has been made. It is a remain constant up to 0.0035 of the strain. First curve is based on the experimental and the code recommended 0.65 FCK, and for 0.67 times the cube compressive strength is concrete strength. This curve is valid for all grades of concrete, and for the design purpose the further gamma m has been divided for 0.67 FCK that has been used for design calculations. Now, the steel stress strain curve. Steel is elastic and linear material up to the yield point, and the line Fy is called as a characteristic curve, and 0.87 is a design curve that is suggested by code Fy by factor of safety 1.15, which comes actually 0.87 Fy. The strain can be calculated directly, design stress 0.87 by Young's modulus. 0.87 Fy by Young's modulus. So this is for the mild steel stress strain curve. So whereas for HYSD bars, there is no specified yield point for HYSD bars as shown in the picture. So the code and experimental results states yield point is corresponding to the 0.002 of the proof strain. The design stress is same as mild steel 0.87 Fy. However, if you calculate strain at this point to be at this point, I mean 0.87 graph at this point, 0.002 plus 0.87 Fy by epsilon s. So this is the strain at this point. Now, so we just learned the stress strain, and now we go to the what are the factored load generally used in the reinforced concrete designs. The load factors are recommended for safe and economic design. Means whatever the loads are there, we further factor that like 1.5 times DL, dead load, plus 1.5 times live load. This is one of the combination. When there is a wind has been combined together, we take only 0.9 tons of dead load plus 1.5 times of the wind load. And similarly, there are many combinations has been provided, like dead load plus live load plus wind load, which is 1.2 times of everything. These are the combinations has been used. The factors are implemented due to the unexpected loads in future, inaccurate estimation of the loads on structure, and unforeseen stress distribution between the members. This is the key information. Consider to factor the loads. So there is another combinations like a dead load plus live load, dead load plus live load plus wind load. These are all actually serviceability limit states. So there are two types of load combinations has been recommended by the code. One is for limit state, one is for serviceability limit state. Now let's go to what are the checks need to be performed for reinforced concrete design. The limit state of collapse, we call it the ultimate limit state. That means you need to check the member or the cross section of the reinforced concrete member for flexure, compression, shear, torsion and tension. These are the checks need to be performed. For serviceability limit state, deflection, cracking, durability, stability and fire resistance. The limit state is a condition that structure will no longer available for service beyond these limit states. That means the structure only can take the loads up to the capacity of these limit states. If it goes beyond that, the structure will not be available for the service, means it may collapse as well. The ultimate limit state is potential modes of structural failure, like a failure may be due to the yielding or rupture. Whereas the serviceability limit state are not the strength based, but it still make structural instability and not able to use for any type of the function. For example, deflection. If it is a huge deflection of the members, let's say your beam is hanging actually, do you think we can able to live in that kind of structures? No. There is a heavy cracking. There could be many other like durability, stability and fire resistance, which has to be pulled by the structure actually. Now we'll look into the another important thing is the minimum requirement of the rebar and the concrete covers. So there are many reasons we might need to provide the minimum nominal cover of the concrete to protect the reinforcement bar. Otherwise the bar will be exposed to the weather, then there will be corrosion and ultimately that will impact the entire structural strength. So for mild exposure, that means the environmental conditions, your structure is mild exposure to the critical environmental condition. What is the environmental condition? For example, your structure is seashore, the exposed to the sea will impact the corrosion more compared to the building constructed somewhere outside the seashore. So if it is a mild exposure of the environment, such environmental conditions, 20 mm is the minimum cover is required to provide. What is the nominal cover and what is the effective cover? The nominal cover is nothing but the edge of the member to the edge of the reinforcement bar. The effective cover is nothing but edge of the beam or column or any cross-sectional member to the center line of the rebar. So for moderate weather 30 mm, severe weather is a 45 mm, very severe is 50 mm. Extreme conditions, we can go for 75 mm. So these covers sometimes not only for the exposed conditions, depends upon the structure where we are actually constructing. For example, beams, even in the normal conditions, 20 mm for example for beams, the same structure for foundation, we may go up to 40 mm as well, because it is required, because it definitely will expose to the underground. There may be water content, all those things will be there. We need to provide the sufficient cover to protect the reinforcement. So these cover, one of the typical thing is to protect the cover and provide the proper bonding to the end reinforcement. The minimum clear cover need to be maintained. Okay, for the effective cover, the nominal cover plus shear reinforcement plus half of the main reinforcement, because it is the center of the reinforcement to the edge of the member. Now, so depth of the neutral axis. So to maintain the section balanced, the tension normally will take care of the bottommost of the cross section and the compression will be the top. So that means concrete will take care of the compression strength, tension will take care of the tensile strength. So now total tension equal to FST is the, or Fy by AST. So that means the yield strength of the steel times the cross-sectional area of the steel will give the tension capacity, whereas the compression capacity is 0.36 times FCK B times X. X is the neutral axis, which will be calculated FST by AST divided by 0.36 FCK B. So this gives the neutral axis depth, neutral depth of the cross section. So in this fashion, we can able to find out the tensile capacity of the cross section and compression capacity of the cross section. Now, for under reinforced beams, steel reaches the yield stress at 0.87 Fy. X equal to 0.87 Fy AST by 0.36 FCK B is the neutral axis depth. So if you divide the D in both sides, you will get XU by D equal to 0.87 Fy by AST divided by 0.36 FCK BD. So what in strain theory, XU by D equal to epsilon Cu by epsilon Cu plus epsilon SV. So whereas the epsilon Cu is 0.0035, which is concrete strain, whereas the steel strain, it depends upon the material we used. Is it mild steel or high tensile steel? For mild steel is 0.0031, for high yield strength 0.0038. So based on, if you substitute these two values over here, the XU by D, which is a neutral axis depth, 0.53 for Fy, 0.48 for Fy 415, high strength yield steel. So these two values is better to recall during the design. So I don't want to go in depth calculations of how this capacities has been calculated, due to the reason most of the code books internationally, they provide how to calculate the capacities by using the formulas for under reinforced section and over reinforced sections and balanced sections. However, over reinforced sections normally will lead to the concrete fail fast, and that will be in sudden failure, which has the more damage compared to the under reinforced sections. So that's why one should avoid over reinforced sections, and in practical mostly we don't allow to design the over reinforced sections. Now these movement capacities, so these are the equations, even though we have touched up briefly, it is already available in the code book. If you can refer, for example, for IS 456, you have an XG. If you refer any international codes, it has these values in built the engineers and students straight away they can use those formulas instead of go to the first principles. So for rectangular sections, XU by D equal to 0.87 Fy by AST by 0.36 FCK BD, which is for balanced sections. So the XU limited values, if you go little one before which we discussed, this is the XU limited values. For Fy 250, the limited value is 0.53. For 415 steel, 0.48 is the XU by D, the neutral axis depth, limiting to neutral axis depth. If the practical XU by D, which is less than XU lim or XU max, then if it is a less than XU lim, then that is called as a under reinforced sections. If it is equal, that is called as a balanced section. If it is greater than XU lim, that is called over reinforced sections, which I already discussed. We don't design those sections. And this MU equal to 0.87 Fy AST D 1 minus AST Fy by BD FCK might not require to remember this equation because it is available in the code book itself. Okay, let's go for XU max, how to calculate these things. For the XU max, for the balanced sections, if you can use this one, the values actually which we discussed for Fe 250, XU by D equal to 0.53, for 415 steel 0.48, for 500 steel 0.46. So the MU values, if you substitute this XU max in this equation, which is provided by the code book, we can able to get MU equal to 0.149 FCK BD square, 0.138 FCK BD square, 0.133 FCK BD square. So what it means, moment carrying capacity of the rectangular cross section for Fe 250 grade steel, 0.149 FCK BT square, which will be even given for any competitive examinations, and also it is regularly used in the practical design as well. So that means when you do the analysis of the structure for the particular beam, we get the actual moment, and then we know which steel we are using. For example, if I am using 415, I can apply this MU equal to 0.138 FCK BD square. With that, I will get a moment carrying capacity of the concrete. Reinforced concrete sections. If this capacity, which is less than the actual bending moment, then the section will be designed for balanced section, and then accordingly the rebars will be calculated. If it is a greater than the balanced section, since we already discussed the over reinforced sections are not a feasible solution, we'll go for doubly reinforced sections. Thank you for watching this video. We will go actual design of the reinforced sections based on this theory in the next videos. Thank you very much.